Hello students, welcome to EPG Pathshala. I am Dr. Anjali Sharma from University of Delhi. Today we are going to talk on module Metal Organic Vapor Phase Epitaxy under the paper Physics at Nanoscience and Technology Part 1. So after completing this module, the students will be able to understand the working principle of vapor phase epitaxy, its reactor components, gas inlet and switching systems in VPE, gas exhaust and cleaning system, environment, health and safety issues of vapor phase epitaxy, and the quantum dot fabrication using vapor phase epitaxy. Metal organic vapor phase epitaxy, or known as MOVPE, also termed as organometallic vapor phase epitaxy OMVPE, or metal organic vapor phase deposition or MOCVD, is a chemical vapor deposition technique which can be used to prepare single crystal or polycrystalline thin films. It is a very complex technique to grow crystalline layers for casting complicated semiconductor multi-layered structures. It is different from MBE or molecular beam epitaxy in the fact that the crystals are grown via chemical reactions and not physically deposited. The process does not occur in vacuum. Rather, a gas phase is introduced inside the reaction chamber at moderate pressure of 10 to 760 torr. MOVPE is a preferred technique in the manufacturing of devices which require incorporation of thermodynamically metastable alloys. For this reason, it has extensive applications in manufacturing of optoelectronic devices. Now students, let us see the working principle of MOCVD. In MOVPE or MOCVD or OMVPE technique, precursors are used in their gaseous form. Ultra pure gas is introduced in the reaction chamber. This gas is carefully dosed with the precursor material in over to deposit an extremely fine layer of atoms on the surface of the wafer or substrate. The figure shown on the screen represents the schematic of the growth process involved in this technique. Crystal growth is favored by the surface reactions taking place on the substrate surface. These reactions involve organic compounds or metal organics and hydrides, which contain the required chemical elements for producing final end products as the reactants. The thin film of the required material or compound semiconductor is epitaxially grown on the substrate surface. This technique can be successfully used to deposit layers of compound semiconductor containing elemental combinations of group 3 and group 5 or group 2 and group 6, etc. As an example, indium phosphide can be deposited onto a heated substrate in the reaction chamber. The process can be summarized as: first, the precursors trimethylindium and phosphine are injected into the reaction chamber. Second, the heated organic precursor molecules are decomposed in the absence of oxygen by the process called pyrolysis. Due to pyrolysis, the atoms to be deposited reach the surface of the substrate. These atoms attach or bound to the surface, leading to the formation of a new crystalline layer at the surface of the substrate. The temperature at which pyrolysis occurs increases with increase in the strength of chemical bonds of the precursor molecules, as a higher energy is required to break those bonds. With increase in the number of carbon atoms attached to the central metal atom weakens the bonds. The diffusion of the atoms on the surface of the substrate depends on the atomic steps at the surface. The vapor pressure of the metal organic precursor is a crucial parameter in MOCVD process. It influences the concentration of the precursor, that is in gaseous state, in the growth reaction as well as the deposited rate. Reactor components. The MOCVD process involves incorporation of reactant gases at high temperature in the reaction chamber. The reaction chamber occurs between these gases owing to the interaction at high temperature, leading to the deposition of the required components on the surface of the substrate. The reaction chamber is made from a material which should not react with the chemical species present in the chamber even at elevated temperatures. Also, the material must be able to sustain elevated temperatures. The reactor consists of a reactor wall, lining, suspector, gas injection arrangement, and temperature control unit. Most often, the chamber walls are produced from the stainless steel or quartz. The chamber walls and the suspector are usually separated by liners made up of ceramics or special glasses like quartz. Water may be flown through dedicated channels integrated with the chamber walls in order to cool the system and avoid overheating. The substrate is kept on the suspector, whose temperature can be controlled. The material used to make suspector must not react with the metal organic compound being used. Graphite is a commonly used suspector material. It can also be coated with special coating layers to avoid reactions with the precursor material or gases. For example, during the growth of nitride and related compounds, the graphite suspectors may corrode owing to the presence of ammonia gas. To avoid this, the graphite is usually covered with protective coatings. A variation of MOCVD also uses cold wall reactors. In such reactors, a pedestal is often used to provide support to the substrate. These pedestals also act as susceptors and is the source of heat in the reactor. As only susceptor is heated, the gases do not react before reaching the substrate surface. Typical materials used to make susceptor are radiation absorbing materials, for example carbon. Contrary to this, walls of the reactors are made from quartz, which is transparent towards electromagnetic radiations. The heat radiated from the hot susceptor may heat the reactor walls to a certain extent. Nonetheless, the walls of the reactor in a cold wall reactor are usually cooler than the susceptor or the substrate. On the other hand, the entire reaction chamber is heated in a hot wall CVD. In some cases, this is desirable as the decomposition of the gases before reaching the substrate may be necessary for deposition of the desired material. Gas inlet and switching system. Specialized devices called bubblers are used to introduce gas into the reaction chamber. In the bubbler, a carrier gas such as hydrogen for arsenide and phosphide and nitrogen for nitride based compounds is purged through the metal organic liquid, which passes through this liquid. The gas picks up metal organic vapors and carriers into the reaction chamber. The concentration of metal organic vapors transported to the reactor depends upon the flow rate of carrier gas and the temperature inside the bubbler. The amount of these vapors is generally controlled with automated controllers fitted with the system, most commonly by an ultrasonic concentration measurement feedback control system. So now students, let us see the gas exhaust and the cleaning system. Toxic waste or the gaseous state of these toxic waste generated during and after the growth process should be converted into liquid or solid forms to be recycled or disposed of. Additionally, tuning the process so as to generate least amount of waste is an important research topic. Environment, health and safety with MOCVD. MOCVD has gained much popularity as nanomaterials fabrication techniques. There is an important concern about its potential impact on the safety of person and environment. This technique involves handling of toxic and hazardous materials not only during particle synthesis but also during the development of the equipment itself. Presently, the safety and responsible environmental care are the significant parameters having extreme importance in the MOCVD based crystal growth of compound semiconductors. Now let us see the quantum dot fabrication. MOCVD is a chemical vapor deposition technique used to grow materials epitaxially. It is widely used to produce compound semiconductors as well. Usually, one of the reaction species containing the required chemical element is an organic compound or metal organics and metal hydrides which has a low boiling point. Pyrolysis of the precursor materials at the surface of the substrate leads to the formation of the epitaxial layer. The semiconductor's growth does not occur in the vacuum, rather with gas in the reactor at a moderate pressure, that is 2 to 100 kilopascal. The third, fifth semiconductors, indium nitride, gallium nitride, gallium arsenide, etc. Second, sixth semiconductor like mercury cadmium telluride or zinc oxide, or fourth semiconductors like silicon carbide or silicon germanium are usually grown by MOCVD. Today it is predominantly used to fabricate solar cells and LEDs in the industrial world. Today's MOCVD GAN growth reactor are developed from the approach of Maruska and Tetigen, which is capable of depositing film with aluminum nitride and indium nitride. The reactors can be of two types, horizontally and vertically. In the case of horizontal reactor, the precursor is injected into the gas chamber from left side and the material gets deposited at the surface of the substrate in the middle of the reactor. For growing uniform films with desirable crystallinity, the substrate is generally inclined with respect to the horizontal flow direction of the precursor gases. In case of vertical reactors, the precursor is injected into the reaction chamber from the upside inlet and the desired materials deposited on the surface of the substrate. The substrate is usually rotated to ensure the uniformity of the deposited films. The gaseous phase in both reactors are removed from the reaction chamber by the carrier gas from the exhaust, usually TMG, trimethyl aluminum TMA, and trimethylinium TMI are used as group 3 precursors. These precursors, usually diluted with H2, react with NH3 at a substrate usually made up of silicon carbide or sapphire, which is heated to around 1000 degrees Celsius. MOCVD reactors for group 3 nitride film growth incorporate laminar flow at high operating pressures and have separate inlets for the nitride precursors and the ammonia to minimize pre-deposition reactions. Figure given on the screen shows complex physical and chemical processes in the reactors. Initially, TMG and ammonia are transported into the reaction chamber to undergo gas phase reaction in the chamber. The reactants are then transported onto the wafer surface. The diffusion and the deposition of atoms and radicals occurs on the substrate surface. Finally, after surface reaction, gallium nitride gets deposited onto the surface. Vollmer and Weber predicted that if the adhesion between the substrate and the depositing crystal is weak, only 3D nuclei can be formed on the substrate. The internal strain in these crystals depends upon the lattice mismatch and can be high or low. This approach of epitaxial crystal growth is termed as Vollmer-Weber mechanism. In this case of strong adhesion between the substrate and the depositing clusters and relatively small crystallographic lattice mismatch, 2D adsorption or phase formation may take place already at equilibrium and even at under saturations. 2D nuclei are formed also at supersaturations and the growth follows a layer by layer mode as predicted by Frank and van der Meeu. This mode of epitaxial crystal growth is known as Frank van der Meeu mechanism. In the case of a strong adhesion between the substrate and the depositing clusters, but significant clusterographic lattice mismatch, the layer by layer growth takes place only during the deposition of the first few mLs. After that, the accumulator internal strain energy due to the strong lattice mismatch compensates the attractive forces with the substrate and internally strained 3D nuclei form on the top of the 2D monolayers. This mode of the epitaxial crystal growth is known as Stransky-Krasnov mechanism, named after I. N. Stransky and L. Krasnov, who considered such type of nucleation and crystal growth phenomenon. For the growth of quantum dots using MOCVD, all three growth modes are used. The most common technique exploits SK growth mode. Self-assembled quantum dots are formed when growing a semiconductor layer on top of a substrate material of smaller lattice constant. Above the critical thickness and under certain conditions, the strain relaxes by forming small islets where at the surface the quantum dot lattice constant relaxes to its bulk value. Generally, a thin layer which is known as the wetting layer will remain completely covering the substrate. The wetting layer forms a quantum well which usually shows photoluminescence below the quantum dot emission wavelength. Quantum dots are finally capped with the substrate semiconductor material to obtain a high quantum yield, that is, avoiding non-radiative recombination via surface states. So students, let us now summarize what we have learnt in this module. We have understood the working principle of vapor phase epitaxy, the reactor components used in it, gas inlet and switching systems, gas exhaust and cleaning system. We also studied about the environment, health and safety issues related to the metal organic vapor phase epitaxy, and we have seen the quantum dot fabrication using metal organic vapor phase epitaxy. Thank you.